There we go. All right. So welcome everyone. Today, May 28, 2021. Welcome for our HBS Lab group meeting for Spring 2021. Today we'll have a summary presentation from all members. They will be talking about their work in short. So we'll go according to the order we have. Now I will pass this to the first presenter, which is Irfan. So go ahead, Irfan.
Okay,
Please
great.
share your screen. Yep.
All right, great. Let me go ahead and share my screen then. Okay. All right. There we go. Is the proper screen sharing? Just want to make sure.
Yep.
All right, great. Sounds good. So yeah, of course, people in the lab that know me, I go by Irfan. I'm a PhD candidate right now in the biomedical engineering field. So I'm leading the iGrab project, which is a design, which is our goal is to design a novel hand orthotic device that's actuated by soft robotics. So different from prosthetic hand and orthotic hand, it doesn't replace a body part, but rather it assists it. So it's important to know that because it's to help aid rehabilitation for those who undergo neuromotor locomotion issues, specifically in the hand. So they need to develop such devices. That the reason for that really comes from the fact that 6.8 million people in the U.S. undergo some form of hand mobility degeneration, which can only be fixed with rehabilitation. And a majority of this population is made up of victims of stroke, spinal cord injury, muscular conditions, accidents, or just old age. So to help these patients, powered hand orthotic devices have been made in research. So in the bottom right, you can see right there, we have first in the left is a MyoPro Motion G. It's an industry-leading device. It's actuated with DC motors, and it takes EMG signal processing to create actuation. And one of the downsides of this device is that it costs $80,000 after insurance. Now you can see in the middle one, it's the NASA Rover Glove. Now this device actually is also an assistive orthotic device, except it's usually used on healthy patients in space to help assist heavy loads and holding that kind of stuff. Now we have the one on the right, the RE Lab 10EXO. It's made by Inichi H. Zurich, and they try to kind of take the downsides of the Myo Promotion G and Master Robo Glove, try to reduce the bulk and costs. And they made another device that's also actuated with a motor and three mechanisms. Now, what we have in our lab is the iGrab. So you can see here on the left side, there are various interpretations of this. So what we have here is the iGrab device. It's a novel hand orthotic device that helps assist patients that undergo hand degeneration. So as you can see here on the left, each of the devices are actuated by what we call twisted and coiled polymer muscles, as you can see down there. So these muscles are nylon fibers that have silver and nickel throughout the entire design. And what we do is we insert voltage and current to help compress and create a strain of the muscle to help actuate the fingers. Now, our current project design goals include trying to have this actuation done with EMG. So what we have here proposed in the diagram is that we'll take an EMG actuation to be similar to Myo Pro. We'll have it sent through a machine learning network, and then we'll have actuation. And this will include a portable device that takes into account different GPU kits, position circuits, actuation circuits, and regulation circuits. The device right now, as you can see here on the bottom, is the most Design 8. It's the most latest device, and we're going to take this device and apply EMG actuation with T-speed muscles that's battery powered and portable. So the iGrab device is essentially going in that direction, and hopefully we plan to have this showing in the future. Thank you.
Great. Thank you so much. Let's give hands for Irfan virtually. Thank you. Any quick question? One question, if any? All right. So this is a highlight. So I think we'll go for.
I have a
Go ahead.
question for Irfan. Uh, so Irfan, how do you plan to reduce the price, as you said, right? Like the present devices which are there in the market, they cost a lot. So how do you plan to reduce the price of your device?
Well, that's a great question, Pawandeep. So TCP muscles themselves, they're very, very cheap in relation to DC motors. You can probably get a DC motor for about $100 that can control the way you want to. TCP muscles, you can probably get a whole spool of thread that's needed to fabricate for about $5. So the fabrication process, training, and annealing process, it's fairly easy, and it's easy to make multiple of these over time. So we plan to use that, and then the rest of the device is a 3D printed exoskeleton, as we discussed, and that 3D printed exoskeleton can be made for each individual user. So that kind of going based off that 3D printing and designing for the user itself, as well as adding TCP muscles, significantly reduces the cost that we talked about, like the Myo Pro, that's about $80,000.
Yeah.
So we are kind of going on the basis of that.
All right,
Great.
Irfan, thanks.
Thank you. All right, thanks, Irfan. Let's go to the next now. Presenter Ishan Navendra.
Oh, sorry. Can everyone see it?
Yeah.
Okay. So my name is Ishan Navendra, and I've been working as part of the iGrab team, and one of the most important parts of the iGrab is the TCP muscle. So today I'll talk about how we manufacture and train our TCP muscles to be used. So the steps I've listed on the slide detail how to create a two-ply TCP muscle. So essentially, two lines are cut to the desired length, and then one end of both of the lines are tied to a motor, and the other end of the lines are tied to a weight. So in this bottom left image, you can see kind of the setup of how the polymer is twisted into proper shape. And then the motor spins until the fiber is twisted into a one-ply muscle, and then the weight is removed, the coils folded in half, and then it is allowed to coil into a two-ply, and then both ends are crimped so that they can be attached to whatever actuation mechanism you need. And then the muscles are trained by running current through the muscles with a weight hanging on one end, which allows for the coils to shrink and then elongate with heating and cooling, which comes from the voltage and lack of voltage, respectively. And a video from the HBS YouTube channel that I can play here. So as the motor twists the wire, it makes that one-ply coil, and then here you can see that one ply is made into a two-ply by folding that, and then it is crimped into place. And then this part details the training of the coiled polymer. And this video uses different voltages and currents, but the setup I'm familiar with used 4 different voltage and current and timing settings, and that's a major difference from this video. So if that's all, is there any questions for me?
Any question? Thanks, Ishan. Let's give applause to Ishan. Any question? Quick question?
What are the applications of TCP muscle apart from the iGrab, which you feel can be done in future?
I think that this could be applied to any sort of actuation and place motors in a lot of different circumstances. So I think it could be used to simulate muscle contraction in like maybe prosthetics, for example. And I think I've seen it used in the underwater robotics division as well. So I think there are a lot of applications to TCP muscles.
Thanks, Ishan.
Great. Okay, thanks, Ishan again. And let's go to the next. Harris. Harris Jelani.
Hey, can you guys see my screen and hear me?
Yep.
Okay. So my work this semester was mostly with IRFAN on the iGrab Hand project. The first phase of the project that I worked on was looking at other prosthetics currently on the market to see what the iGrab Hand could take inspiration from. So I found that the most advanced prosthetic currently on the market is the Deka arm, which aims to have the full functionality of a human limb while maintaining a similar weight. The design model of this arm was rugged enough to handle a drill while delicate enough to pick up a grape. The arm comes in three configurations, which attach at the radius, the humerus, and the shoulder, and have respectively 6, 8, and 10 degrees of freedom. So as you can see, the user has a pretty high degree of control over the movements of the arm. It comes with 6 pre-programmed grasps to simulate common hand movements and operates on inertial measurement unit and electromyographic control. IMUs are units that are placed in the shoes of the user and allow them to use specific leg and foot movements to control the device, while EMG is a type of sensor that's applied to the residuum where the amputation occurred and interprets electrical signals from the nerves, sending this info to a master control module on the wrist, which then interprets the information to move the arm. Deka devised an algorithm called endpoint control to interpret this information and essentially allow the arm to find the most effective way to get from point A to point B. Because this arm has so many degrees of freedom, it would be hard for a user to have to input each individual movement to get the arm where it wants to go. So the arm actually calculates the way to move for the user. However, because it's got such high-level technology and such increased functionality, there's also a pretty hefty price tag, and this arm costs over $100,000 per limb. In opposition to this, the iGrab Hand, which is an orthotic device being worked on by the Tedeschi lab, is a much more accessible and low-cost alternative for amputees. It uses the TCP muscles worked on by the lab and only costs around $1,000 for the hand and control system, as opposed to the $100,000 for the Deka arm. And even for other functional prosthetics, you're looking at anywhere from $20,000 to $50,000 or higher, so definitely much more accessible in that respect. It's highly lightweight and compact, but because the material is 3D printed and the TCP muscles are weaker than the motors used in other powered prosthetics, it has a lower grip strength and carry weight than the average prosthetic arm. Another advantage of the iGrab Hand is the fact that it can individually move all fingers besides the thumb, giving the hand itself 4 degrees of freedom, as opposed to the 2 or 3 degrees of freedom often used in functional prosthetics. And it's currently being worked on to implement EMG. Once this is implemented, that means that the user will essentially be able to control the hand, as it will interpret electrical signals from the arm, and this will contribute to how easily it is able to be used by the user. So overall, the iGrab Hand sacrifices some functionality and power for accessibility and precision, and represents a much easier to access choice for amputees in a market that's often dominated by a couple large companies.
Great. Thanks, Haris. Questions? Quick question? So I think, let me comment on the cost also, that some of the electronics are the one that makes it expensive. But obviously the TCP muscles are extremely inexpensive, which lowers the cost.
Yeah, I think that's the big advantage of the hand, is the fact that it relies on these very easy to use, low cost muscles.
Mm-hmm. Great. So this Deka Hand is popular. So it's been in publication, many ASME journals. It's been featured many places. So we may have to look more in this kind of device. In terms of one thing we have to look is like the noise, also the weight of the device. I expect it will be heavier because of motors and stuff like that.
Yeah, I think I have the information on one of the documents. I can send that to you.
Mm-hmm. Great. All right, let's move for the sake of time. Let's move for the next. Daniel, right? So Pawandeep, is Pawandeep or
Yes, sir.
Daniel and
Okay, I can't
Daniel's not
see
here, right?
Daniel. No, I can't
Okay.
see Daniel here.
So next is Ishan is also not here. So Eric is in his own way. So we will skip to that. And so iGrab team is done almost. But if others come, we will check. Okay. Now I think Drew. So we'll go to Drew now. Oh, he's part of iGrab team somehow, as well as he has his own. So I'll pass to Drew now.
Okay, sorry, I had to unmute.
Uh-huh.
Okay, slideshow from beginning. All right. So, as many of y'all might be aware, heart disease is and heart failure is one of the leading killers in America and the world. I believe last I checked, this was pre-COVID, it was in the top 3 leading causes of death in America and top 10 in the world. So it's a major problem. We know that. So over the years, there's been a lot of different options and solutions for that. Different kinds of valves have developed. We started with simple, we've gotten more complicated. However, if you look here, you'll see that the natural valve, this one right here is a natural aortic valve. And if you see here, it's not just a simple linear structure that's just a straight leaflet. And the problem is that most polymeric solutions use a relatively straight leaflet structure at an angle very much steeper than the natural condition. So currently what we're investigating is with the use of certain smart materials that can be conditioned and designed to react to certain pressures to behave more like the natural. That's mainly what we're going for. We're investigating how to accomplish this. We're involving things like metal reinforcement of the elastomer and similar ways of production. But the overall goal is to have a cheap, effective, easily surgically implantable aortic heart valve. Thank you.
Great. Okay, thanks, Drew. A quick question. I think can you explain briefly the simulation, Drew, that you have on the left side?
Oh, my bad. So sorry. Yeah. So the simulation here, what we're doing is we're trying to determine at what thickness will we have the optimal response to the average pressures found in the human body. So although we went all the way up to 50, even though that never happens, if that happens inside the human body, you're dead. But we did that as a factor of safety. And we're trying to make sure, we want to make sure that we want to get the right size of elastomer so that we don't have breakage or tearing of the valve, but that we also have full opening as much as we can get. We want the valves to fully open to not restrict the blood flow through the valve. So we're tinkering and adjusting the different values to find the sweet spot of thickness so that we have the correct thickness and correct angle relative to the valve. So relative to the outer ring of the valve.
Great, thanks. All right, so let's give a hand for applause to Drew. All right, so any questions? Quick question.
I have one question.
Mm-hmm.
Drew, what sort of muscles are you trying to use to actuate the valve? And then how much actuation strain optimally are you looking for?
Well, first of all, I don't know what the optimal strain percentage. I don't remember that offhand. However, the other question I can answer very easily is that we're actually not. So we actually don't want any active actuators because then that would require a power source. And natural valves have no way of manual activation. It's all passive activation due to the pressure differential. So what we're wanting is just a material that can be trained to respond specifically to certain pressures. So we're investigating that as to whether that might be some type of smart material, whether it's just polymer with certain materials that with certain properties that we've added. It's all being investigated, but at the end of the day, we don't want any kind of actuation that's going to require any kind of power source.
Cool.
Yeah,
Thanks.
that's what I thought too. Initially, I thought so we're gonna use some actuators to open it, but it's the pressure gradients that opens the natural one.
Okay.
On the other hand, the benefit of smart materials is that they can be modulated. Their stiffness can be changed. You can make it stiff, like in the smart material class we talked about martensite, austenite, right? They have different modulus of elasticity. So that is one way of also changing stiffness, So one way of changing stiffness is geometry. Another way is material. If you can change material, then stiffness can change. So I think we are still investigating that, right?
Yes.
Yeah, right, Drew?
Of course, yes. I'm constantly investigating it, just trying to find we've got the goal clear in sight, and we're just investigating what materials are a good starting point for initial tests. And then, like all research, we'll keep investigating until we find what we need.
Yeah. And we'll be working with UT Southwestern also on this, because some people are working on research in this area at UT Southwestern. So we'll keep in touch with them.
Wonderful.
Great. Thanks, Drew. Miles. So now we'll go to the next, Onan Ahmed. Onan, can you share your screen about mobile platform? Okay.
Hi, can you hear me?
Yep.
Cool. So I'm Onan Ahmed. I'm a computer science master's student, and I've been working for the past 2 semesters with Abhishek, Darshan, Pawandeep, and Dr. Tedesi on helping them with the HBS 1 socially assistive robot paper. So the HBS 1 shown in the bottom left corner is our lab's 3D printed humanoid robot. But right now the problem is, although it has a lot of degrees of freedom, it's really stationary. It's very difficult for it to move around because it's a bipedal right now. We're trying to make it the top left with a robotic platform on the bottom to give it more powerful, to help it do more things, which will make it a more powerful platform and a more useful assistive robot. Right now, we are thinking that the HBS 1's applications could be healthcare, military, that sort of stuff. To start off with my market search that I did this in last semester, I had to look through the HBS 1 paper and find the requirements of what the mobile platform had to, the characteristics it had to have. It had to have a 5 kg payload and around a 20-inch height and about 14-inch or greater diameter for the base to prevent tipping and to allow it to be mounted. So these graphs on the right, the tables on the right side, are an abbreviation of what we are adding to our paper. The top two, left and right, are the commercial robotic platforms, and then the bottom left and right are the open source mobile robotic platforms. There's a huge difference. The commercial ones are much more powerful. They're much more expensive, around 9 to over 50,000. I'm saying that because I abbreviated what we showed in the paper, so we can't really tell which is what, but I did a little price comparison relative. The open source ones are much cheaper at around $500 to a little over $2,000 for the most expensive. The problem with the open source is they're not very powerful, but they're much more customizable. Overall, our decision was to go with a DFR robot. It's very open source, very customizable, and it fits our payload criteria, our height requirement, and we can add any type of computing or battery. We can add which battery we need, which makes it very tailored to our use case. In the future, we're trying to make the platform a little smarter to make decisions using technologies such as machine learning to help it assist patients a little bit better. That's what I've been working on this semester.
Great. Thank you so much, Onan. Any quick question?
I have a quick question. I was just curious, what specific medical fields, like, okay, so OR, general nursing, elderly, what like specific fields do you feel like this has the greatest potential for?
So right now, we've been concentrating a lot on Alzheimer's rehabilitation and just helping them, like more of a conversational type thing and helping people get medication. It's been done, but the difference is from the existing solutions, and ours is a 3D printed and low cost robot, and it utilizes the TCP muscles also in the hand. I think the iGrab project is trying to be incorporated or something like that in it. But right now, we've read a lot about Alzheimer's rehabilitation.
Very, very good application. Very nice.
Yeah, just to add on that, so basically for assisting in home care, home environment, this robot can do pick and place. That's why we do that activity, pick and place, some kind of manipulation to help those individuals.
Yeah, and then we did talk about, or we're talking about a pick and place of getting medications for certain patients and giving the right medication to the right patient.
Yeah. Great. Thanks. So thanks, Onan. So let's give it up. Let's give the hands for applause and move to the next. Next is Abhishek Singh.
Hello, everyone.
Yep.
So I have been working. I'll share my screen first.
I'm spotlighting everyone presenting, the presenters. So we'll see them. Can you see them magnified? Presenters?
No, sir.
Okay, maybe it's only for me. Okay, go ahead. Yep.
Yeah. So I have been working on development of the social assistive robot that Onan also just talked about briefly.
Can you make it full screen, please?
Is it not full screen yet?
Not yet, I think.
Is it now?
Hold on. Not yet.
Abhishek, you have to share your screen, I think. You have shared the presentation only, probably.
Oh,
It is shared. It is shared, but
I'll share it again.
okay. After this is Ovi. After Abhishek.
Okay, is it full screen now?
Mm. Not full screen. Maybe do you have two screens?
No, I have only single screen.
Okay, can you click that one, the bottom, to make it full? I'm not saying I'll say full.
Yeah, on my screen it's showing as full. Right?
That's fine. Okay, let's go
I
ahead.
think you can click slideshow. I think that's gonna show the full screen. Slideshow on top.
Nay. Slide. Go to the
Slideshow.
slide.
In the top, beside home, it's after animation, it's slideshow.
Okay.
I think.
Yeah,
And
from the beginning.
from beginning. Did that work?
From the beginning.
Yeah,
Click the begin. You did it. Okay, I think
yes.
that's fine. Let's continue with this.
Okay, so yeah, so I've been working on the development of socially assistive robot. This is the HBS robot. So currently, this robot comprises of different mechatronics and electrical components, and the body panels are made from 3D printed materials, and we are incorporating 6-ply TCP muscles for grabbing actions and pick and place experiments. So we were able to perform a pick and place experiment in the previous semesters. So the main motivation behind development of this robot is, according to CDC, the number of people entering old age is increasing significantly, and by 2060 they are projecting an increase in about 60 million Alzheimer disease patients suffering from this disease, while at the same time the number of caregivers are reducing, and there will be a lot of openings. So the purpose of such a robot is to assist those caregivers and provide healthcare services and improve the quality of healthcare provided to the patients. So currently, you can see the robot just grabbed the cup from one spot and placed it at a different desired object target position. So how this robot works is, currently it uses a traditional computer vision system in which it differentiates red, green, and blue color. So currently in our program, we just painted the cup as green color, marked as green object, and then it grabs a picture from the camera mounted on the frame. It's a Logitech camera, and then it calculates the centroid of that area of the green color, and then tells the robot that where the cup is located, and then uses inverse kinematic equations to reach the cup, grab it, and then place it to the desired location. So currently, the way this is set up is not fully automated. We have to trigger the grabbing action manually using the 6-ply as it is connected to the PWM driver through NVIDIA Jetson. So in the future, our goal is to make it fully automated, use machine learning techniques as well, and make it into a mobile platform as well, so it is more useful, as Onan had mentioned before. So that's the current situation of this robot.
Great. Okay, a quick question for Abhishek. We've been discussing this at least every other day, every week, at least twice, to complete this paper. But the application is great. So this Alzheimer or assisting as a socially assistive robot, SARS. So one thing is that 6-ply, we have one publication on 6-ply for jellyfish, but not for other robotic application. You guys may have to look Armita's paper, because that's the only one we have regarding 6-ply publication. I checked yesterday.
Yes, sir.
All right.
Yes, sir.
Okay. So let's go to the next. Let's give an applause to Abhishek.
Thank you.
And thanks, Abhishek. Let's move to the next. So we have Ovi now. Let's change a little direction on 3D printing. All the research we've been doing are related to each other. For example, the social robot is entirely 3D printed. When we say entirely printed, most of the part, except few components, the social robot. And this robot is unique, the one Abhishek showed, and Onan is unique because printed at that size, an age of 7 years old kid size. That's so big. You know, most 3D printed robots are very small. So we are talking about adolescent size robot. Okay, so Ovi, it's your
Okay.
territory now.
Professor, like Irfan told me that it should be on 2 minutes, so I've already recorded one.
Yeah.
So I'm gonna just share that one.
Okay.
Okay, thank you. Can everyone see?
Yep. Did you share audio option?
Yes, Professor. Hi, I am Alishla M. I am a PhD student at the Mechanical Engineering Department of UT Dallas, and I am working at HBS lab under the supervision of Dr. Yunus Tadisi. My research topic is additive manufacturing of elastomer using custom-made 3D printer in soft robotics. We all know that additive manufacturing of soft materials such as elastomer has received substantial scientific and industrial interest in recent years because of their using soft robotics, low material compliance, and material properties. So here we can see this is our 3D printer setup. In my research, a low-cost, custom-made and open-source 3D printer is being used to print a highly stretchable elastomer that actually has adequate tensile strength and can also be fabricated to build an actuator. And by using the custom-made 3D printer and elastomer with different mechanical properties, a presentably substantial and thicker 3D printed structure has been printed in our research. We tried to scale our structure gradually from smaller to bigger to investigate the strength and strain of the printed structure. Meanwhile, temperature also varied to reduce the curing time for the 3D structure. Here, this is the biggest 3D printed structure we have printed so far. Moreover, we are actually trying to develop a functional and factual method for additive manufacturing of soft robotics 3D structures. So our future goal right now is to print bigger, thicker, and complicated 3D printed structure. For that, we need larger heating bed, and we also want to fabricate different type of 3D printed soft actuator structure by using 3D printing structure, 3D printing stretchable elastomer. Okay, so that's all I have, and we have done my research by using our hands. Everybody knows. So the thing is, we need to purchase a gear set to do this automatically.
Mm-hmm. The syringe, to be clear, right? The syringe,
Yes,
that
syringe
support part is you did it by supporting manually.
Yes.
Yeah. Great. I like the quality of the video. That's great. So the one that's printed, illustration is great, and 100mm size printing is one good thing. So overall, that's a great activity. Okay.
Thank you, Professor.
Quick question. So, yeah.
I have one question, sir.
Mm-hmm.
Hi, Ovi. Like how easy or how difficult is it for you to 3D print different probably what do I say, different dilutions of silicon? Like if it is quite diluted, how easy or how hard, or if it is much more thicker, how easy or how hard it is?
Okay, so the viscosity plays a big role in here. So if it is like less viscous, it printed really easily. But sometimes it pour a lot of materials, then like it creates a problem in your structure. So it's just a trial and error method, in my opinion. So you keep using those, keep mixing silicon thinner, and you will find like which one is optimum for your research.
All right, all right. So can't we actually change the speed of actual printing
Yes, we can.
if the viscosity changes?
Yes, yeah, viscosity you cannot do in the software. You can like do it by mixing all the materials, because the one I used to use before, the actually Dr. Armita used that. That one has the different viscosity, and the one you purchased, the dyed one, it has the different viscosity. So previously we needed to mix silicon thinner, but now we have that one. We don't need to mix silicon thinner. If we mix silicon thinner, it becomes like very it poured very easily. So that's the thing actually.
Thanks, Ovi.
Yeah.
Mhm.
And
Yeah.
we'll talk that in detail in the lab. So
Sure, sure.
and all the speed and everything, it can be changes in the software. It's like all the
Yeah.
options are there.
Hmm.
They have a plenty of option in the software.
Great.
Thanks.
Thank you, Ovi. So let's give hands for Ovi
Thank you.
also. All right. So let's go to the next. Sribankar.
Um, I'll share my screen first.
Mhm.
Are you able to see it?
Not
Not
yet.
yet.
Okay. Able to see it now?
Yes.
Yes.
Okay. Mm, so hello, I'm Sribankar K. I'm a master's student in mechanical department, UTD. So my so I'm currently have worked on reviewing the soft actuators. So like thermally actuated, electrically, pressure, magnetic, and pressure and electrically stimulated actuators. And I'm currently working on the work of Fluido jelly. So this Fluido jelly, as the name suggests, is a biomimicry of a jellyfish. So we are using eight pneumatic actuators to control the movement of the jellyfish. So till now we have achieved only up and down movement of the jellyfish, and we are working on the multi-directional movement control of the jellyfish. So till now, so we have used CO2 and air compressed actuation systems for um, uh, moving the jellyfish. But we are now looking forward to using the surrounding water so that we can actuate it even better.
Great. Can you share back to this slide? I think look up that I will say that ethanol in silicon, electrically stimulated in your graph, soft
Yes,
actuators.
sir. Yes.
I think look up those. That's good. Also, we haven't looked so far Shape Mary polymer or any. We are free to use any of the actuators, okay, as long
Yes.
as we get good results. All right.
Yes, sir. So can you see it?
Yeah, I can see that.
Okay.
All right. So yellow is your favorite color? Is that
No,
no?
no, it's nothing like that.
No, I'm just looking just based on your first slide. So, anyways,
No.
just it's just a coincidence, right?
Yeah.
Um, okay. Any other question? Any comments? Question for Shubankar? I think you have looked so many interesting literature this semester. Also, very interesting from publication. I think you can also use those for future demonstration, what you have been doing, your
Yes.
activities. Okay. So many nice publications from science, nature, and smart materials and structures. So there is another paper coming in smart material structure using some kind of vapor to actuate. I saw it yesterday. So you guys may have to look that vapor basically. I think it's published already. Okay, any comments, question? All right, let's give hands for Sribankar and move to the next. Dorsa is not here, so Natalie is not here too. So Sanjana, I think, is the next. So we have 1, 2, 3, 4 more presentation.
Hello, sir.
Yes.
I'll just start presenting.
All right.
Okay, can you see my presentation?
Yeah.
Yeah. Hi, I'm Sanjana.
Can you
Yes,
remove
sir.
me? My picture is on your slide.
Actually, yeah. Can you
Okay.
still hear me?
Yeah.
Yeah. So hi, I'm Sandhya N and I'm a master's student from Biomedical Engineering Department, and I'm working with Professor Tadisi in the HBS lab. And currently, I'm working on two major projects, one for the iGrab hand and one for the underwater robots. And so I'm working on the sensor components of both the robotic systems. So the first one I would like to go into is the underwater robot, where you can see on the left side is the circuit for the underwater robot. We want to do a kind of water quality parameter testing on the robot, because underwater robots are mainly used for environmental condition testing, and like in military you can use it for spotting other things in the water along with fishes and other things. So you can see that there are the conductivity probe, dissolved oxygen probe, and the pH probe, which is basically water quality testing parameters, and the components that have been used for that. And there's also a temperature probe, so that we can do a correction of all the pH, dissolved oxygen, and conductivity according to the current temperature. So that's the circuit for that. And we are trying to add Wi-Fi functionality to this module, so that we can send this data to the server and it can be monitored along each day and over time. So, coming to the iGrab project, on the right hand side, you can see the sensors that are being used for the iGrab project. We are planning to implement an IMU device, which is basically an accelerometer and a gyroscope, which can give the current orientation of the wrist. Secondly, we're using the strain gauge, which will be implemented at the joints of the fingers, so that we can see the amount of strain that the orthotic device is going through in each grasping mechanism. And the third one is the force sensitive resistor, which will be placed at the tips of the fingers, so that when there's a grasping mechanism going on, we can do an analysis on the amount of force being exerted on the devices and the amount of force required for that orthotic device to do that kind of grasping action. And all of this would be connected to an Arduino, and through Bluetooth, we can send it to an app on a mobile device. So, yeah, thank you.
Great. Thanks, Sanjana. A quick question. One very short question for an hour. Very short. I mean, 1 minute. I'm just joking.
All right. So I have one question for Sanjana. Sanjana, if I use the IMU sensor, which is not waterproof, in the jellyfish robot or the underwater soft robot, how can we put it in water without actually damaging it?
We can, the plan right now is to use a polyurethane coating that's basically a spray. So it's a two-step process. Like we can use the coating on the IMU device and then cover it with a heat sink type material. And like we need to use a kind of a heat treatment to stick that heat sink onto the IMU device, and it will be waterproof then. Like two steps, polyurethane and covering for the device.
Thanks, Sanjana.
Great. That's a good question too. So thank you both, Sanjana and Pawandeep. All right, so let's give hands for Sanjana and move to the next. Let's give it up. Ripudaman. I don't see Ripudaman here.
Professor, he's not here.
Okay.
He's probably stuck somewhere. So probably we will have to skip him.
Yeah. So let's go to Akash.
Hello everyone, my name is Akash. Let me just share my screen. Is it visible?
Yeah.
Good evening everyone, my name is Akash. I'm a graduate student in Department of Mechanical Engineering at UT Dallas. I'm working on underwater soft robotics project under Professor Tedesi and Pawandeep. So basically we are trying to develop a project, a robot that can operate underwater and without any mechanical actuations. So we have the inspirations on our left hand side. You can see this is the crypto jelly created by the HBS lab. This is a squid bot from University of California, San Diego. This is a fish developed by MIT. These are all softly actuated underwater robots. Now we are using muscles for our bot. We are using three different types of muscles: the TCP, the SMA, and the fishing line muscles. Now this is how the fishing line muscles are created in the lab. This is the setup we have. We coil the muscle and then we wrap the muscle with the conductive wires, preferably nichrome, and that's how the muscles are actuated. We have a few actuation setups on our right hand side. The first one is inspired by a squid, a squid like fish. The other one is inspired by a jellyfish. So we're working on the both of the actuation systems. On the bottom left you can see the powering systems that we are working on. Basically the every other bot that is present in the market now has a limited operating time because of the battery that it carries. We are aiming to power our bot with the photovoltaic system, which will generate the power with the help of sunlight, and even practically, I mean virtually, it will make itself as give itself an infinite range. We will be implementing a number of sensors such as electromagnet and the sensors like Sanjana showed to have a different applications for the bot. And on the right corner we can see that the experiments we have been carrying out to check how the muscles and how the muscles react to different environments. So this has been this has been the work we have done so far in this semester. Thank you.
Great. Wonderful. Quick question now.
Yeah, Professor.
Anyone? I think that's a great summary that you gave, Akash.
I have one question, sir.
Yes, go ahead.
Okay, Akash, what do you think if we use salt water rather than normal tap water for the swimming actuation using the fishing line? How will it work?
Yeah, we have tried that. I think a couple of weeks ago we have in the experiment you can see on the right corner side there is salt water. Now the salt water is conductive and
I'm
it
sorry, Akash. If you can just make it full screen and show the video.
Yeah, that would be good.
I don't think this. Just a second.
Yeah.
Hide. Okay.
Yes, just bring
Yeah.
it forward. Yeah.
So we have clean water, then salt water. I think in this setup, the wires were connected directly to the weight, and the weight is a pure metal. So it started, started started the electrolysis of the water at very high rate, and thus the current was lost and was not conducted through the muscle. Thus the actuation was very minimal. Then we separated the weight from the muscle and in the third setup. Now this I mean this kind of helped because of the separation the metal was not helping in the electrolysis, but still the current was passing through the water and electrolysis was happening, but because of the bypassing of the current, the actuation was not as good as the actuation in distilled water. So
I
that
see.
was the
Thanks,
Yeah.
Akash. Just to add to it, Professor,
Mhm.
when we used salt water, what we actually observed was that the voltage decreased a lot. But yes, a certain amount of input current had to be increased in order to get the same sort of actuation. But then the voltage decreased a lot.
I see. So it looks like, you see, this is what is happening. The current that's supposed to go to the actuator, it is going to the solution. So
Yeah.
we are losing that current. That's why the resistive heating is less in this situation. So that's why. So probably we may have to encapsulate the actuator separately from the surrounding somehow. That way we'll isolate when it is operating in salt water. You know, but that's a great side by side comparison, which is really nice. I'm seeing it for the first time, so that's good.
Thank you, Professor.
All right, so thanks, Akash. Let's give hands for Akash and then move to the next, last but not the least presentation. So everyone, we are almost done. We are a little late for about 8 minutes, but we're almost done. Okay, so Pawandeep.
Yes, sir. I'm sharing my screen. Are you able to see my slides, sir?
Yep.
Okay. Okay, so here goes. Okay, so my name is Pawandeep Singh Matharu. I am a PhD candidate at the Department of Mechanical Engineering in the University of Texas at Dallas, and I'm working in the HBS lab under the supervision of Dr. Jonas. So basically, what my research areas are, I'm working on various fields. But firstly, I'm working on underwater soft robots, and I'm working on artificial muscles. I'm working on humanoid robot, and in the future, I am determined to uh, generate energy harvesting system for the underwater soft robots also. So as you can see on the right hand side of my slide, I am showing the various work which has been done in our lab and also outside of the university, which has been really successful in the field of underwater soft robots. So at the top, by Al Mubarak et al, we did crypto jelly, and it showed really good swimming with the help of artificial muscles, SMA especially, and in the just below it we can see SOFI from MIT. Though the design is different, but we can learn a lot of things from it in actually producing a futuristic soft robot that can swim efficiently underwater. Below that, we can see a robot which actually swam to the deepest point of the ocean that is the Mariana Trench, and this was done by a group of Chinese scientists. Just over to the left, I have put up a graph that I reviewed. So I just put this graph because it shows the various research done in this field of underwater soft robots and the swimming height of these robots with respect to time. Then I move on to the artificial muscles. Our lab is specialized in working with artificial muscles of various types and using them for various applications. So here I'm showing the basic process of how we fabricate the artificial muscles like the fishing line muscles, as well as the 1-ply, 2-ply, 4-ply, and 6-ply TCP muscles. Just below this figure at the very end on the bottom right, you can see the 6-ply TCP, and just onto its left, the fishing line muscles, which are being used for various applications. Now, as I mentioned, I'm also working on the humanoid robots. So here we did a simple experiment with just one finger for deformation, and we are trying to use both these muscles in this finger, which in turn will be integrated to become a hand. This is a rendered picture of the hand, which we will be using to actuate, and this will in turn be used in a humanoid robot for various applications in the medical field. And as a futuristic work, as Akash mentioned earlier, we are certainly looking for developing an underwater soft robot that can swim throughout the day, 24-hour, without the need of it recharging or changing its batteries. So we are trying to go for solar energy because it is the most comprehensive and well-known form of renewable energy that we can find. So we are trying to work with solar energy to develop a robot which can be powered 24/7. Thank you.
Great. That's wonderful. So wonderful summary that Pawandeep about underwater robots and robotic hands. Any quick question for Pawandeep? Which robots do you appreciate the most so far from the literature among all the soft robots? I know it's a very hard comparison because each robots there is a unique feature. So, but just as an opinion.
I would say that I would choose two robots. One is from our own lab. That is the Fluido Jelly. I don't know why, just the speed probably. The Fluido Jelly, and number two is SOFI, because because SOFI is so well manufactured and fabricated. It really and actually we are trying to do that. We are trying to manufacture or make a robot which can be manufactured of similar design over and over again. I think SOFI can be done like that. So these are the two robots.
Yeah, I think it's autonomy also, the powering unit, electronics, and swimming, biomimicry. So many things are in that.
So many things are there.
Yeah, great. Thanks, Pawandeep.
Thank you, Professor.
Thank you. Last call. Anyone missing? Last call. So that's what you see in a bar, right? So by the time it's going to close, I think everybody presented here. So thank you so much. Finally, I would like to say thank you so much, everyone, for making this happen and for a nice summary that you gave. I'm so proud of each of you for your contribution to the HBS lab and for yourself. So we'll continue our activity so that we go to the bottom of this, solving the fundamental problem in robotics, and so that people can use it for either healthcare, could be education, military, and also other applications. Okay, so thank you so much, everyone. And I will leave you to enjoy your Friday night. And thank you so much.
Thank you, sir.
Thank you, Professor.
Have a good evening, everyone. Thank you.
Thank you, sir.
Thank you so
Thank you,
much.
Professor.
Thank you, sir.
Thank
you,
you,
sir.
Obi. Thank you, Sanjana. I'll be staying for a few more minutes if anybody wants to discuss. And I'm gonna meet each of you based on case by case. But for now, we'll end this meeting. Okay.
Yes, sir.